I'd like to introduce the speaker, and a lot of you will know one of our own, Dr. David James, and he's going to talk about industrial process automation and introduction, so it'll be educational, I trust. And anyway, David is actually very experienced in this subject, but I'll let him tell you why he's so experienced on that. But I hope he tells you he's got a degree in nuclear engineering or something. So, but anyway, so over to you, David.
Right, thank you. Yeah, good evening. Nice to see you all here. My background wasn't quite as Mike described. As a physicist, I started my career working on the design of nuclear reactors for submarines. But every 2 years, the MOD changed their mind and cancelled the contract, and so we started on something fresh. So eventually I thought I'll go and work on the design of civil power stations, which I did. And after 2 years, you can guess what happened. The contract was cancelled, and we were about to start on something new. So that's when I moved into the area of industrial process control. And for the next nearly 40 years, that's where I stayed, working for a number of international suppliers of control systems and getting around the world a fair bit. You can see down the bottom there, 2017, which is when I produced an early version of this talk, which was aimed at sixth formers to give them some idea of some of the engineering aspects. I've added to it a lot since then, but I'm afraid I chose this particular style of the book for that audience, and when I came to try and change it, it messed everything up. So I'm afraid you're going to have to make do with and put up with the page turning. It's just too complicated to change. By the way, does anyone here work in industrial process automation or control systems? Oh,
well, I've got a bit of a history of being associated with them.
All right, oh, good. You can help me answer some of the difficult questions then when we get to the end.
Geography, not history.
So what I want to do is just try and give you a flavour of industrial process automation, just sort of skim over the surface. And we'll try and cover these things. I talk about industrial processes, and it will be worthwhile just clarifying what I mean by an industrial process. We'll look at some of the engineering disciplines who are involved and collaborate to get a process plant up and running. And all these different engineers produce information, produce data, and I've just called it client data because that's the information that comes to the automation engineer who's going to produce an automation system. Then we'll delve into the system itself, looking at sensors and actuators, so sensors measuring various quantities, parameters on the plant, and actuators actually influencing the plant in terms of valves, pumps, motors, and so on. Then we'll look at control and monitoring systems, including then the operator interface, before going on to some of the concepts and the schemes, the way in which these systems are made to control a plant and the tools that are available to the automation engineer. Okay, industrial processes. Well, here we have a few. The pointer, the red pointer is almost, well, I can't see it, so it's too small. But up the top there we have a refinery. This is a cheese manufacturing plant. That's a pharmaceutical plant, a brewery. Sometimes you do some quite useful or interesting projects. That's Shoreham Power Station. So that's a combined cycle gas turbine. That's a nuclear power station and obviously an offshore oil rig. They're all examples of industrial processes, but they basically fall into two classes. There's what I've called assembly and an industrial process. So I just want to make it clear that an assembly is something that really can be disassembled. So if you think of a car or a phone, Now, I know there's welding and there's glue and all sorts of things that make it difficult to take them apart, but in principle, the various components keep their sort of identity. And often robotics are used, particularly in the electronics manufacturing and other things. An industrial process, however, it can't easily be undone. Now, I know that making petrol in a refinery is really just breaking apart the various molecules that are already in there, and in principle they could be put back together. But what you do with all the additives and so on, I don't know. Processes in an industrial sense tend to be fluids and powders that are piped around and mixed and react. So you've got chemical reactions, blending, separation process, and so on. And there are a number of things, like almost everything we're here. These seats were the basic plastic before the moulding, and it was made in one of these processes. Similarly, medicines, petrol, and chemicals. So we've got those two different types, and it's the latter that we're going to concentrate on. And just two examples of these processes. They generally break down into two types. There are the continuous processes, so they have a constant feed of material, and they really aim to maintain a steady state. Refineries are a good example. They want crude oil flowing through constantly. The only time they'll change is if they get a different source of material, a different type of oil, one that's heavier or lighter or has more sulfur or whatever, and they'll want to change the parameters. But generally, they want to keep it as steady and as efficient as possible. And then there's batch processing, and that really is manufacturing a quantity of material, and usually requires a recipe with a list of ingredients and some production procedure. So cheese, for example, pharmaceuticals, the plastics, they're all batch processes, and there are quite different requirements for the two types of process plants. If we take the refinery process as an example, you know, you're probably all aware, it's a distillation column. Crude oil comes in, is processed in various ways. Steam comes in to heat it. And then the different fractions, different molecules that are within the crude oil condense out at different temperatures. And so a whole set of grids allow the different materials to be taken off. And as I said, that's a continuous process with a constant feed of oil. A pharmaceutical process that's just another example, just really to point out that a refinery, there's lots of other bits and pieces, and not just the column. The column may be the most difficult part to control, but there's a whole load of other ancillary equipment that's required in the system. When we come to something like pharmaceuticals, then generally there's something that is rather like a reactor there. This one, has an agitator, and it's obviously got some heating jacket around it. There's some bulk material tanks that are used to feed it. The output is going up through a crystallizer and then a slurry tank and so on. And there's lots of other pieces of equipment that are associated with the plant. That reactor, of course, is not just a vessel. It has, as we said, an agitator, but it's got steam and cooling water, nitrogen feed, because often materials need to be processed in an inert environment, particularly where there's the possibility of some electrical sparks, and various other valves and pumps associated with the vessel. So each of the vessels that are in a basic schematic then have much more detail associated with them. And just as an example again of something a little more complex, here we have another pharmaceutical plant. There's 3 reactors in parallel, all being fed by the same set of tanks, and the materials then coming again through other equipment This is the fermentation process. So they can become quite complicated. One recipe of a product can be used multiple times and running in parallel. So you have often parallel trains that all need to be managed. So hopefully that's just given you a flavour of the types of industrial process, at least what I am referring to as an industrial process, and the sort of automation systems, therefore, that we're going to be talking about. To put all that together, there's a number of disciplines that are going to be involved. Now, I'm going to ignore things like architects and civil engineers who are going to build the buildings. I'm going to ignore the operations people who are making the product and the maintenance people who are going to keep the plant running. But to actually produce the, define and realize that plant, it usually starts with chemical engineers who will scale up lab scale experiments to, they know the basic chemistry, but now they have to make it work for large quantities of material. There are then, of course, the process engineers, and they will start to say, okay, we have these requirements of the materials and what reactions we have to put in place. But now they look at the plant in a general form and do the basic top-level design, working out what vessels are required, what sort of functionality is required of those vessels, and providing that, as I said, that top-level design. Mechanical engineers will come along and they'll design the more detailed arrangement. So they'll decide what materials are actually needed for that particular product. They'll decide where the pipes are going to run, how it's all going to be laid out, the physical structure of the system. And the instrument engineers, we've got all these pipes and tanks and pumps and motors, but we need to measure lots of things. So all the instrumentation that's going to be required is sorted out by the instrument engineer. And of course, there's a sort of iterative process here. It doesn't all happen in steps. But all that information, together with the one I'd forgotten, the electrical engineers, who are going to now work out, well, how are we going to power all these various things? Where are all the cables going to run? How do we make it a productive plant? And the information generated by these people is what's required by the automation engineer. It would be nice if all these things happened and they were 100% complete before the automation team come in. That, of course, never happens. On the one hand, people try to do as much as they can in parallel. So from early information, they'll start developing the other systems that are going to be implemented. And of course, there are always changes. People decide that, well, actually, we need another vessel here because we're not going to get the throughput. So they add in another one. We're not going to use on-off pumps, we're going to use variable speed pumps. Changes happen all the way through the process, and everyone involved there has to adapt and change what they've done. Now, of course, all these people then provide a set of information that I've referred to as client data. So a process flow diagram, that's a process engineer will produce. This is high level. So he's got a couple of tanks, he's got some valves. These are symbols that are used for valves. There's a heater, there's a compressor there, some filters at the top. So at top level, how the plant is structured and how it's going to be connected and how material is going to flow. The mechanical engineer and the instruments engineer are going to produce what's called a P&ID, a piping and instrumentation diagram. So now we're starting to get more detail. So we take one vessel, in this case just a tank, but now we have temperature measurements and temperature control. We have level transmitter and level indication, and so on. So they define all of the details of the instrumentation that's going to be on the plant. There are also things that other people need. For example, for each pipe, it will say how angled it is from the horizontal, if some natural flow is required. The instrument engineer will also produce what's generally referred to as an instrument index. And basically for every transmitter, every valve, every device that's on the plant, they'll produce a database giving its reference number, its name, the type of device it is, its range, various parameters associated with it. So that when all this information is put together, together with some control narratives, which again are developed by the process engineers and the instrument engineers, then there's enough information for the automation system to be defined and implemented. I thought it worthwhile just to put some of the acronyms up. I may use some, I may not, but you often find these SCADA, the Supervisory Control and Data Acquisition. If you think of, I guess they started when you had oil fields distributed around the desert. You needed to collect information from each wellhead, bring it back to a central point, and allow operators to view it and possibly change things. So they have these remote telemetry units, just some electronics to read the analog and digital inputs, to drive some digital outputs, and then communicate over some sort of network to bring it all back to a central database and allow the operators to view that. Distributed control systems are a tighter sort of system. Controllers based around the plants, again, reading those input signals, sending output signals, and all communicating with each other. Remember, the RTUs are only communicating back to the SCADA database. So the distributed control system now is providing control across the board, and again providing data for analysis and data for and a view by the operator. A process automation system is an oddball, really. It's sort of rather like a distributed control system, but generally made up of more standard individual blocks that can be put together, often using devices that could be used in their own right, on their own, but now integrated into a system. Programmable logic controllers, I don't know whether any of you have come across relay logic in your work somewhere, but the PLC was designed really to replace relay logic. Rather than have lots of relays all wired up so that if a push button's pressed, then various things happen, or if some alarm is produced from some part of the plant, then actions can be taken. And basically, they produced a system that would provide an electronic relay logic system. These days, they're actually used more extensively, whereas it started off really just looking at a replacement for ladder logic. Nowadays, a lot of people use them as the basic controller for a control system. And of course, human-machine interface, they all require some means of accessing or providing access to the information by operators and by engineers. Okay, well, what I really want to do now is just talk about those sensors and actuators. The sensors are measuring things, temperature, flow, pressure, whatever. And the actuators are pieces of equipment on the plant that are going to change things, pumps, motors, valves, and so on. And in the middle, of course, you've got a control system that's going to read the inputs, make some decisions and drive the outputs. Typically, the sensors cover, well, that's just an example. There are other types of measurements that take place as well. But if we look at temperature, for example, then usually, most commonly, it's either thermocouples or resistance thermometers. So thermocouples, as I'm sure you're aware, two different bits of metal. They produce a small current depending upon temperature. And that small current can be measured and give an indication of temperature. Resistance thermometers, I mean, you could all think back to our Wheatstone bridges when we did A-level physics or whatever, but it's that sort of idea. A wire with resistance changes its resistance with temperature. So you can use that to measure it. When we look at flow, two major types, although again there are others. If you pass fluid through a small hole, you get a pressure differential across there. If you measure that pressure differential and take the square root, it's proportional to the flow that's going through it, which is quite handy because they're often used then for measuring the flow of various materials. A more complicated item is a turbine meter. So it's rotating and you count the number of times it goes round to give a view of how much is flowing through. And some of these can be really accurate. I mean, coming back to the oil field, I suppose it's wherever tax is going to be paid, they have to measure the amount of product that's produced very accurately. And great lengths are taken to have highly calibrated meters and controllers and test the flow meters periodically. There are other flow meters, for example, a positive displacement meter. Fill up a volume and then empty it. Count how many volumes you fill up, that's how much fluid has gone past. If we look at one of the other types, level, as an example, there's a whole host of things. I mean, from a simple sight glass along the side, where an operator can go and look, to radar systems, to systems that go up and down and detect when they reach the surface. There's ultrasonics and various switches to show that the fluid has reached certain levels. So depending upon the application, there's a lot of choice for people as to what they can use for level transmitters. If we go back and now take a look at actuators, I'm just going to talk about valves and motors. Then valves, I've called them solenoid valves, and I'll explain why in a moment. But basically, that's an on-off valve. It's either open or it's closed. Right. On the other hand, we have a control valve. In this case, it's a butterfly valve. It's going to rotate to allow varying amounts of fluid to pass through. And I've said pneumatic because these are all very well, but if you need them to be in an environment where there's a chance of a spark and there is flammable fluid, flammable gases or powders, then often pneumatic systems are used. And often solenoid valves are called solenoids because the control system just drives a solenoid, and that changes allows the gas to go through to drive the valve one way or another, so that in the process plant, then that's a hazardous area and you're not going to produce a spark. With pumps, it's a similar sort of idea. You've got on-off pumps and you've got variable speed pumps and a whole range of different types. And similarly, motors to drive agitators or to drive fans or whatever. So there's a whole collection of actuators that are used on the plant. Now to that box in the middle that is going to read those inputs and drive the outputs. You've got various types of control systems. Manual, of course. Man sat there turning the wheel and moving it. Well, that was done for a long time. And in fact, you may be able to remember people talking of walking the panel. They'd walk up and down, looking at the dial, looking at the gauges and the dials and twiddle things as they went. Pneumatic systems, I've never actually worked on a pneumatic control system, but as well as having the pneumatics to drive the valves and so on, you can get controllers that will allow you to do various things with the pneumatic system. And I say, you probably know more about those than I do. If we look now at a single loop control, let's go back to something very simple, a tank with a temperature indicator and a valve that's going to change whatever it is we're passing through the jacket around the vessel, and a temperature indicating controller. That is a loop. We give the controller a set point, say we want the temperature to be this amount, and it measures it, looks for any error, opens the valve or closes the valve to regulate the temperature of the jacket around it. And that's single loop control, and probably, I don't know, 90%, perhaps more, of control on process plants are just single loop controls. And I'll talk a bit more about that in just a moment. And they often get put into boxes that can be put onto panels. It just deals with that single loop, or some of them have multiple loops or multiple single loops. We mentioned the SCADA system, this collection of remote telemetry units reading sensors and using some sort of communications network to send the system back to the SCADA master and thus the HMI that the operators are going to use. A typical system might have these remote stations, these RTUs, using some communications network, and it can vary to be just a dial-up modem or a radio system or hardwired cables. From some of the offshore platforms in the North Sea, they use tropospheric scatter to get signals back to the shore. But then there's some device that is controlling the network, and then a number of servers for the database and operator interfaces, and of course possibly some link into wider networks. And for a distributed control system, this is a typical example. We have a range of controllers along the top there. They're all communicating amongst themselves on, in this case it says industrial Ethernet, and optionally redundant. Often these communication systems are redundant so as to increase the availability. And each of the controller is reading inputs and sending outputs via modules that are wired to those devices that are in the field. A typical signal from analogues, like a temperature or a pressure, will be a 4 to 20 milliamp signal. I mean, they've been used for years. It's 4 to 20 so that if it drops below 4, you know there's a problem. The wire's been cut or something. So that's been a standard for a long time. These days it's tending to be supplanted with communication systems. So you hang all the devices off a communications bus or a number of different buses and do digital communication rather than the analog 4 to 20. But the communication system that's connected in all the controllers then will also have other operator stations and database systems associated with it. A brief word about operator interfaces. When I talked about walking the panel, that's a typical panel that the operator would walk up and down, keeping an eye on certain things. And with experience, they would know what to look out for. Because sometimes there can be quite a lot of information on there that needs to be viewed by the operator. And typically on those panels, they would record the history of information by using a paper chart recorder. So a pen leaving an ink trace on the paper, which always runs out when you don't want it to. Yeah. But they, of course, were replaced by digital versions. So now in their panel they have some fancy graphic system that shows them how things are moving over time and allows them to recall data and do various operations on it. Much more versatile, but still to some extent fairly limited. The operator screens themselves, now when I started we had characters that we would write onto the screen, and the character could be a block of a certain colour that if we did enough of them and made up a pipeline, or it could be a line, or it could be text, but it was pretty rudimentary. Then we went through a lot of development on graphical user interfaces, and people got carried away, and they produced garish things that they thought looked pretty, but were not necessarily as informative as they could be. More recently, people have decided that a basic operator interface should be boring. It should be boring and it should be grey, and it's only when something goes wrong that you start introducing colour, so as to alert the operator to that something needs happening. And that sort of alerting the operator is often done by using process alarms. It would be the case of often using annunciators. So a set of illuminated buttons with legends on them, and everything was well. It was sort of grey or green or some suitable colour, and when things went wrong, the colour changed, it started flashing, the klaxon went off until you accepted it. That again, with the introduction of visual display units, transformed into something more like this. Again, using colour to indicate the status of signals, and this time now giving you a bit more information about what's actually happening. And coming back to our grey, boring visual display, again, those alarms are indicated on the display so that people can home in more easily. And although alarm displays are on almost every system, it tends to be by using the graphical interface that operators can decide really what's going on. Now, of course, these operator interfaces are usually put into control rooms, and it could be something as simple as a couple of screens, a keyboard and a mouse, and one operator sat there operating the plant. On the other hand, it could be like this, which is from a refinery in Mumbai. So we have operator stations, a whole series of them, and we have wall displays that, if I remember correctly, were not actually as good a resolution as this screen here at the time that it was first installed, but that was some time ago. So a whole range of operator interfaces, a whole range of how you put together a control room, and the number of hours spent deciding exactly what form of console was going to be used seemed to go on forever. No one could ever make up their mind. So we've had a brief look at processes. We've looked at some of the engineering disciplines and the client data that they produce. When I say client, I'm talking from the automation engineer's point of view. We've examined a few of the sensors and actuators and some of the control and monitoring systems and operator interfaces. I'd like to just finally cover some of the concepts and schemes that are used in the control systems. Because so far all we've got is a set of boxes that are set up and wired into the plant. We have to implement some control. And we looked at manual, and we've mentioned single loop control, which we'll look at again a bit more in a moment. And I want to introduce the idea of PID control, which I'll explain, and some other types of control. So, single loop control, just as we described before, and in this case, there's two loops. There's a level indicator and a controller operating an inlet valve, and there's a temperature controller, again operating the steam valves for the heating jacket. And for each of those, the operator will set a set point, the target, what it wants it to go, what you set your thermostat to on the wall at home. And that will introduce, so I've lost it, here it is, the sensor coming back is measuring temperature or whatever, and there'll be an error, there'll be some difference. And the feedback controller takes that error and produces some requirement that is sent to the plant. Feed-forward control is slightly different and used probably a lot less often, but it allows you to predict what you think might happen. For example, I was involved in the automation of a PVC plant. Now, PVC is one of those products which at some point in the process becomes exothermic. In other words, it starts generating heat, and it does it quite quickly. Now, you can work out or get an indication of when that's about to happen. So what you want to do is put some feed forward into it so at that point, so as to try to keep this exothermic reaction in place. Now, these single loop controllers tend almost invariably to be what's called PID control, proportional, integral, derivative control. So it's basically saying that the change that I want, when I've got that error, the output I want to send to the plant is made up of three terms. The proportional plant, so if the error is that big, then I send out a certain amount. If it's only that big, I send out less of a change to the plant. The integral term says, well, if my error has been there for a long time, then I probably need to do something about it. So I want to look at the integral of that error and adjust the output that I'm going to send to the plant appropriately. And then the derivative, the rate of change. So if it's starting to change quite quickly, then I want to react quickly and increase the output that I'm sending to the plant. And these three these three terms make up that PID control. And the K is then some factor that you can adjust so as to try and tune your loop. For example, if you choose different values, you will get different responses. So if I'm asking for a step change, then depending upon the values that I enter for those constants, I will get different responses from the plant. So if, for example, for difference, you can see the K for the proportional term there changing, then it initially, depending upon the value, it will overshoot and oscillate. And interestingly, it will never actually get to the point that you want if you just use that term. If, however, you add a bit of integral control, now it's still got that oscillation, but it's brought us closer to the target value that we want as the constant is being changed, the parameter is being changed. And if you add some derivative control, then if you choose your parameters right, you can get something that is very close to what you actually want, that step change. We talked about single loop control. So the other major type of control that's implemented is what's called cascade control. So here, for example, we have a flow controller. It's reading a flow measurement, and that's the PV stands for process variable, and it's going to drive a valve. But its set point is coming from another loop, a loop that is looking at level. So if the set point for the level isn't being reached, then it will give a set point to the flow controller to adjust the flow. So we have cascaded control. We have one control loop providing the set point for another loop. And that's used quite often in the systems. There are other types of control that are less frequently used. Multivariable control, where there's more than one parameter that you want to take into account. So inline blending, going back to that brewery, the liquor, which is, the beer that's produced is blended in line with liquor, which is basically water. So they're just watering down the beer. But to do it on a continuous basis and in line, it requires some special control. We've mentioned distillation columns, and there's lots of parameters there that need to be considered in the overall control rather than just using single loop or cascaded loop controllers. Similarly with gas liquid separators. And there are generally what are referred to as model-based controls. So you're taking the physics and trying to model what's happening using the values and using that model to adjust your control. So having all the hardware and having, in theory, how you're going to control various parts of the plant, that's all very well. But now we need to look at how that is implemented, how that's defined and implemented within a system. We've mentioned relay logic. And there's a very simple example. If someone presses the start button and these valves are in a certain state, then some motor will be driven or whatever. Basically, you've got a power rail on the left and a ground rail on the right, and if power goes through, then some action will be taken, which was basically how a physical relay system worked. And it's just a software implementation of that. And that's often used, as I say, on machine control. So a bottling plant, or we have a supply, we've made our Coca-Cola and we're going into the bottling area, and the bottling area will often use relay logic to control the operations. One advantage they have is that they can operate pretty quickly. They're limited in the complexity of what they're doing, and they can have a very fast cycle time. So fast-moving machines lend themselves to that sort of implementation. When it comes to continuous processes, there are two sort of standards that are used to specify what's required. I've used this sort of terminology, this sort of notation on other diagrams. This is an ISA standard, so a temperature transmitter. With a square box around it, it's a temperature controller. The I means indicating. A flow controller, well, this is probably then an orifice plate because it's got a square root sign there. A control valve, an on-off valve, something that's open or closed. Actually, with the Y there, it probably indicates that it's a safety valve. So the majority of process plants tend to have their definition made using that sort of notation. So on those P&IDs, the piping and instrumentation diagrams, there'll be that notation used. The other notation is SAMA. As far as I've come across, I've only seen it used in the power industry. It may be used elsewhere, but I've only seen it in the power industry. But it's the same sort of idea. We've got the field with its transmitters, we've got the field with its outputs, and in the middle we have, in this case, a PID block, square root coming in, and the output being driven into the field. So again, a type of notation that is used by the process engineer and the instrument engineer to define what control needs to be implemented. Then we come to batch control. Now this is, as I said, batch processing and continuous processing share a lot of ways of operating and a way of defining things. But the batch process has another level of complexity on top. You define your process as have a physical model of your process. You break it up. So a valve might be a control module. Several valves together operating will be an equipment module that will be defined. A number of control modules and equipment modules combined around usually a major vessel will be a plant unit. And it's designed so that you can run a batch using a particular recipe on whichever unit you want, whichever unit is available that can operate in the way it wants to, without having it hardwired or hard-coded for that particular vessel. The other standard that's measured here, as I said, the batch control, ISA 88, is the sort of Bible for that. But there's also an IEC standard that says, well, how am I actually going to implement this control? This is an example of a sequential function chart. It's really just saying steps and transition. So it says from the start, if that transition is true, then I can go on and do the next operation. Here we have two transitions in parallel. Each one will allow it to pass through. So steps and transitions, rather like a state diagram, but just a slightly different nomenclature. And that's another type of configuration that's defined by IEC 61131, which is function block diagrams. So if you take an analog input, well, you need a piece of code that's going to read the value from the 4 to 20 milliamp signal, that's going to convert it into engineering units, that's going to perhaps do alarm checking on it, and then make it available to the rest of the system. And so you'd have a function block, one of these, that has that functionality. And you can pull it off a standard function block, put it there and connect it to your field and to other parts of the control system. And this sort of function block diagram and the sequential function charts are very useful for engineers, particularly when trying to track down problems, and being able to look at the graphics and look at the associated block diagrams and documentation to see exactly what's happening, where signals are going, what is right, what is wrong. The sequential function chart. What I described before, just this is a tool that enables the engineer to build that set of steps of operation with the various transitions. And here one of the transitions is actually being defined in terms of some ladder logic. So they interoperate, they combine together to allow the people to specify them and to people generally say configure. End users don't like you say code. They don't want code. So configuring standard algorithms would be fine. And in fact, on the first system I worked on, we called them algorithms. These days, it's a term that is taught to our 5-year-old children when they're starting to look at computing about an algorithm and what it means. We've been using it for 40-odd years in the control systems. As I mentioned, that quite often we have we've got continuous type plants and we've had batch type plants, and quite often there needs to be a combination of the two. For example, on a cheese manufacturing plant that I worked on in Denmark, the milk that comes in in batches, that's put in tanks, but it has to be pasteurized before it can be used. And the pasteurizer is a continuous process. You can't stop it. So you've got a batch plant making batches that are going to end up being converted into blocks of cheese, but with a little bit of continuous plant in the process. And so the appropriate buffering has to take place to be able to combine the two. Another example is my boss one day called me in and said, would you like to go to Malaysia for a week? Oh, yes, I thought, yes, I've not been to Malaysia. I'll go for that. It turned out that our Singapore office had sold a large control system for a petrochemical plant in Malaysia. What they hadn't realized until they actually had been given the order was in the middle of all these continuous processes, there were 3 batch processes, and they didn't have any experience with batch processes. Now, I should have realized that I couldn't do justice to the thing in a week. So 9 months later, I was still there. Luckily, then I was able to hand it over to another person with batch experience. But often people are caught out thinking that a batch control process is just like a continuous process, and it definitely isn't. Okay, configuration tools. So we've started by looking at industrial processes. Hopefully you have an idea of what I mean, at least by industrial processes. We looked at the sensors and actuators. In between, we looked at the different disciplines of engineers that will be involved. We've looked at the collection of data that is put together to help define what the control and monitoring system is going to be all about and what it's going to do. And we've looked at some of the typical systems, just at an overview level. We've looked at operator interfaces of the various types, very briefly. And we looked at some of the control concepts of PID loops and of the standards that are used to define the type of control that's required on a plant. When I first developed this, I put that slide in to say to these youngsters, if you want to travel the world at someone else's expense, then automation engineering is for you. These are the places outside the UK that I've visited or worked as part of my career. And so I thought, well, if I can't convince them by the technology, then perhaps I can convince them by the travel to think of control systems and being an engineer in that. Okay. I'm hoping that I've given you a bit of a flavour of industrial process control, process automation. It's a pity we didn't have more students here from the college who perhaps may have found out a little bit about what opportunities are open to them. But okay. Questions?
Questions?
You mentioned batch processing as a specific, is different from continuous processing. I was talking to some process engineers and I said batch processing, and they said, no, not batch processing, campaign processing.
Ah.
Has that got a very specific meaning?
Yes, by batch processing, I mean the basic sort of methodology. They tend to run, from a production point of view, they run campaigns. So it depends who you're talking to exactly. And it may be that in the 13 years since I've been retired, the terminology has matured a bit or changed. But yes, certainly campaigns. When I mentioned that ISA 88 standard, then it talks of campaigns within a batch system. So yeah.
Questions?
How old is all this? When would you say was the first automated process?
Well, let me see. 1969. In about 1975, I started in industrial process control. Started off with a PVC plant that we were automating. And we had memory, individual boards full of memory chips. The older, at that time, I know I'm old now, but the older engineers said, "You used how much memory to do that?" We did it in only half the time, half the amount of memory. And they were ferrite core memories. So for a decade at least before I started, then control systems were in place and operating. They tended to be mainly on continuous processes because there was a big demand from the likes of oil refineries and so on. And it was just as I came into it that batch processing was really starting to take off and the standards were starting to be developed. I don't know if that helps, but it's been going for some time. Yeah. Yep.
Another one? Go ahead.
I've heard from speakers a couple of times, at least, that the UK is behind other countries when it comes to robotics. How do we compare when it comes to this kind of automation?
I started in this field for Ferranti computer systems. So it was a civil part of Ferranti. They tried to do everything themselves. They made their own processors, their own operating systems, their own compilers, everything. They went out of business. They couldn't compete with the large American companies. So there has tended to be a dominance of US-based companies. I worked in Crawley for one of them, what was started as Foxborough, which is based in Massachusetts. They were bought by Invensys, and then Invensys was bought by Schneider Electric. So they're sort of amalgamating, they're consolidating. There are a lot of smaller companies around. I mean, Eurotherm is a good one, locally, down on the south coast, who are, I've forgotten who owns them now. They were owned by Invensys for a while, but there are smaller companies, but the big systems that seem to be predominantly US-based. So the UK has a lot of expertise, and it so happens that batch is one of the areas where we seem to have a lot of knowledge about how to control a batch process. But otherwise, yeah, the UK is more a user of other people's products.
You had a question?
Just an observation, really, David. When you listed all the different disciplines involved, I guess the one that seemed to be missing is the process safety people who look at the control system and then want to change it and add this and add that.
Yes, when I said I hadn't included architects and civil engineers, I should have said I haven't included the safety engineers, because there's a whole parallel stream of activity that is aimed at safety systems. Now, I mentioned relay is often used in safety systems. One of the worst experiences I've ever had in Kazakhstan, taken onto the plant and seeing a relay logic system, hardwired relays, with lots of plastic coffee stirrers pushed into the relays to stop them tripping. There's a whole series of systems that started with relay logic and has gone now through automation with triplicated systems and duplicated systems and so on. And it tends to be, yes, there might be HAZOP type studies on the control system, hazard and operability studies, but then there's a whole set of safety studies as well. So, yeah, no time for going into those as well. Not that I'm an expert, well, not an expert anyway, but not that I know a lot about safety systems.
Can I add to that? Because my first control job, or sort of control job, was in Philips in the 1960s. And we were asked to develop a logic that was not affected by radioactivity. And it was to control the nuclear reactor. Basically, it was a safety circuit to switch the whole thing off. And what they were worried about was if there was a large amount of radiation, then you needed something which was not affected by a radiation in order to switch the whole thing off. So we were working on magnetic logic, which had no semiconductors in it. And so the safety issues have actually been addressed but usually they were called scram circuits. So you could see what the safety mechanism. It was a last resort to try and show things down. But certainly the logic has changed over the years. And another thing which was before you really got going, David, was back in it was probably in the 60s, early 70s when I worked for Philips, and the logic circuits, the industrial control circuits, they deliberately used special techniques on the transistor circuits, for even the ones operating the relays, which was to use higher voltages and everything decoupled hard, because there's so much noise from motors in a factory that it was interfering with the logic which was supposed to be controlling things on that. So, things have progressed a bit since then, I think.
Yes, and I didn't mention magnetic logic. That I'm not sure if it's still going, but it was on the market and was used quite a bit. And of course, down at the more detailed and smaller level, there's embedded control. So control that's actually written in firmware down into systems. So there's a whole plethora of different types and levels of control. So.
Any more questions?
Back to the list of disciplines. One of the things I thought you were going to say but you didn't was mentioning systems engineering. Now, is that because systems engineering is behind many of those individual disciplines? Is it hidden in one of those disciplines, or is it to the side?
I think over the years, all of those disciplines took on a systems view. I mentioned that they sort of collaborate and that there's iteration, and taking a systems view across all of it has been the way that people started working. I know that there are people who specialize in systems engineering, and it applies to a whole range of things, not just control systems. But yes, it's something that did become more uppermost in people's minds and change the approaches that were used.
If I may again add to that, the systems view is a good way of putting it, because I certainly know, Bernard Challen, who was an old colleague of both us and IET College, he used to say, well, systems is only project management. Systems engineering. It's only project management. Call it project management. So, so I think actually a system view is the right way, and certainly in some of the customers that I was dealing with in latter days, systems of systems was becoming to the buzzword. But it's all systems thinking. But
yes,
the only difference, systems of systems, is layered thinking.
The value that I found in it.
Sorry?
The value that I found in systems engineering.
Oh yes,
It's not that it gives you the answers, but it allows you to ask the right questions. So I can ask an electrical engineer, about his scheme. I can ask the chemical engineer about his scheme and find out why I've got 44,000 gallons of output missing from your process. Oh yeah, because that gets fed back. You didn't tell me that. Now I've asked you the question based on systems analysis. You can give me the critical piece of information.
Yeah, and there are a whole load of tools, sort of nomenclatures and way of describing systems that have been developed over the years. People tend to find the ones they like the best and then use those.
Okay, if there are no further questions, it remains to me to ask you to thank David, but in a moment. Normally we present him with the certificate, but
I didn't.
Shall we pass on that?
I think we'll pass on that, yes. We normally give them to our speakers so they can show their wife that they were actually giving a talk. But my wife's seen me preparing this, so she knows what's happening.
But anyway, so because we're not giving him anything, I would ask you to, well, show your appreciation very loudly instead. But I think it's been an excellent talk. It's certainly been quite nostalgic for me because I cut my teeth in various aspects of control engineering and actually taught sample data control systems. But anyway, that's a different thing. So I think we've had a really nice introduction. It was called an introduction. Thank you very much, David, and show our appreciation.
Thank you.